So here we go again with the video on introduction to eigenvalues and eigenvectors. In this video, we are going to introduce the notion of eigenvalues and eigenvectors and how to evaluate them. Let's again begin with our traditional approach. Consider the transformation matrix A, B, C, D and some vector of elements x1 and x2 and now we move ahead with a question. And what is that question? The question is, what are the vectors that are just purely scaled by this transformation matrix and not rotated? That is one point of the question. What vectors are purely scaled by A, which is a transformation matrix, and not rotated? And the second part of the question is, by what value or values are they scaled? So these two are the questions we are going to address in this video essentially. And the first point of the question, these vectors which are purely scaled by A and not rotated are called eigenvectors. Eigenvectors. And the values by which those vectors are scaled are called the eigenvalues. Now moving ahead. When we say that the vectors after being transformed are purely scaled, what do we mean? We can write it like this, right? Like the A matrix, if we multiply with the vector x, it's going to give some transformed vector, right? Xt, as we've seen. But this xt is essentially going to be some scalar times that actual vector, right? So our new transformed matrix, is essentially just some scalar time. Our new transformed vector is essentially just scalar times the original vector. So we need to find these kind of vectors. And this scalar value by which the original vector is scaled is called eigenvalue. Moving ahead to find these, how do we do that? We'll take the very definition of it, what we have written just. So we need the Ax to be some scalar times x. We need to find such kind of x. We need such kind of x's, which are vectors. And those vectors are called eigenvectors. and these lambda values by which those eigenvectors are scaled are called the eigenvalues. So if we write this A again, which is A, B, C, D, and the vector X, which is having the elements x1, x2, this is just some scalar times the original vector x1, x2, right? So we take the right hand side to the left because this x vector is common in both A, B, C, D times the x minus lambda times the x is 0. This gives A minus lambda, B, C and D minus lambda times x equal to 0. Now if you notice, here is a very important part. This thing here represents a set of homogeneous equations. Meaning RHS is 0 for every equation, where each equation is represented by each row. Now we come to the theory of linear algebra and notice a few things, which are, the first is, for a homogeneous system, for a homogeneous system of equations to have non-trivial solution, the rank of the system must be less than the total number of rows in the system. Say rows or say equations, both are same, right? Because each row represents an equation. And when this happens, this would mean at least one row exists such that that row is a linear combination of one or more other row or rows in the system. And when this happens, the determinant of the system is necessarily 0. Having said this, we implement it here. So our system of equations was this: a minus lambda b c d minus lambda times the vector x equals 0. This was our system of equations, right? So the determinant of a, let's say this is no more a, right? Let's say this is a lambda. The determinant of a lambda is 0 would imply a minus lambda b c d minus lambda is 0, and this would mean uh, a minus lambda times d minus lambda minus bc equals 0. And again, if we open the brackets, that would give us ad minus lambda times a plus d, then we get another term of lambda square, yes, that's how it is, minus bc equals 0. If we rearrange it to make sense, lambda square minus lambda into a plus d plus ad minus bc equals 0. Now this is a quadratic equation. Above is a quadratic equation to be solved for lambda values. We get two values here, right? Because this is a quadratic equation. We get two lambda values. Now let's say we get lambda 1 and lambda 2 as the solutions. Then moving on to finding the corresponding eigenvectors also, because this lambda 1 and lambda 2 are nothing but the eigenvalues, the scaled values, or the factors by which the eigenvectors are scaled. So at this point we know by what factors the eigenvectors, if they exist, are scaled, but we don't exactly know the eigenvectors yet. So we go on to find those eigenvectors, and we do that by substituting these lambda values in the governing equation. So the governing equation is this again. Governing equation is this: a minus lambda b c d minus lambda times the x equals 0. So this is the governing equation. Then we find the eigenvector corresponding to the first lambda value. Eigenvector corresponding to lambda 1. Let's say that is x transformed 1, or yeah, let's say that x transformed 1. Then, or yeah, so what we do is we reduce this governing equation. What governing equation? We first substitute this a minus lambda 1 b c d minus lambda 1 times the x equals 0, and let's call this as a lambda 1. Now we reduce the a lambda 1 into the row reduced echelon form and find out x lambda 1, x lambda 1 of 1 and x lambda 1 of 2. So here, what does this represent? X lambda I j. I is the suffix of lambda and j is a different thing. I represents the ith eigen value, and yeah, that's it. And j represents jth element of the eigen vector. This is the notation I am following now. Let's go with this. And once from the row reduced echelon form, we directly can compute or calculate the x lambda 1. X lambda 1 is the eigen vector corresponding to the eigenvalue lambda 1. And similar process is repeated to find the other eigenvectors. And this is how we find the eigenvalues and eigenvectors of a given system of equation, or let's say the transformation matrix. For a given transformation matrix, this is how we find the eigenvalues and eigenvectors. So this is it for this video. Thank you.